increase over time, while the derivative function shows the growth rate of the fruit each day. So the bioscience problem chosen in this project is understanding durian growth, during planting, and how the environmental factors can affect the fruit development. Farmers sometimes face some problems such as unstable water and unstable weather, poor fertilizer timing, and low food quality. Therefore, this system helps farmers predict the best growth stage and harvest time more accurately. So, studying in this bioscience problem is important because it can improve food security and agricultural productivity. By understanding the growth rate of durian, farmers also can reduce food waste and improve food quality and manage fertilizers, lower food quality. Therefore, this system helps farmers predict the best growth stage and harvest time more accurately. So, next I will explain the important points in this HTML. First, the logistic growth model, FX. So this is the example. This formula represents the overall growth of the durian fruit mass from the early stage until maturity. Next is the derivative function f inverse x. This function shows the rate growth of the durian when the graph reaches the inflection point. It means the durian is growing at its maximum speed. Besides that, there are interactive sliders in HTML. Users can adjust the maximum weight growth coefficient and growth midpoint to simulate different environmental conditions such as fertilizer quality and weather change. So this is the formula. So lastly, one recommendation to improve this HTML project is by adding a real-time weather or an AI prediction system. So this can make the simulation more realistic and useful for farmers in the future. So that's all from me. Thank you.
Assalamualaikum and good night. My name is Nuzara binti Bakar. My metric number is F2-5A1821 and I'm a researcher in food security. Today I want to share something interesting about how mathematics, specifically calculus, actually plays a hard role in securing our country rice supply. We'll be focusing on a very popular local rice variety called Mardi MR297. And I will show how we use data modeling to figure out at the perfect time to apply fertilizer and predict our harvest yield. Now we look at a rice field. We usually just see the plant getting taller day by day. But from a scientific standpoint, the way the paddy boosts up its dry biomass actually follows that we call a sigmoidal curve or an S shape. This basically means that in the beginning, it grows pretty slowly, then it enters a mid-season mitigation phase where it explodes in growth and finally it plateaus out as the crop reaches maturity. Now we move to the mathematical and bioscience formulation. First, simulation the biomass function. So how do we put this pattern into numbers? We use this logistic function based on real empirical data from RD. We have three key numbers here. First, 12.0 tonnes per hectare. This is the maximum genetic yield capacity for the MR297 variety. It basically cannot grow past this point. Second, we have the growth rate coefficient, which is 0.08. And third, day 55. This is the exact midpoint where the crop experiences its fastest growth acceleration. Two is instantaneous growth rate, the derivative. This is where calculus comes in by differentiating the original formula using the quartet and chain rules. We get F, which gives us the instantaneous daily growth rate. This new formula is super important because it tells us exactly how many kilograms of food the plants are synthesizing on any single day. The graph turned into a near bell curve, and its absolute peak is right on day 55, like this. And last, why must a food security specialist master calculus? First, resource allocation efficiency. Is fertilizing rice based on a fixed calendar is wasteful and cause nitrogen runoff, poisoning local water bodies like the Mudra River system. By accommodating the derivative, scientists identify peak nutritional windows, allowing precise target application. Second, forecasting and planning. By integrating drought rates or tracking the second derivative, acceleration or deceleration, authorities like Pedibira's National Berhad can predict bumper crop or yield deficit months before harvest, securing reliable rice imports or pricing policies. Last, climate resilient selection. When breeding climate adaptive paddy cultivars, researchers compare derivative parameters. Values did not repeat in the initial growth, representing aggressive competitiveness against wheat and shorter maturation pace. That's all from me.
My name is NURALIA BINTI ROSDAN. So the summary of the bioscience problem is in Malaysia, maximizing the yield of fresh fruit bunches (FBP) from oil palms is critical for land use efficiency and economic food security. As an oil palm plantation nature, its annual yield follows a biological curve. It increases rapidly during early maturity, peaks, and then gradually declines due to aging and canopy shading. The application models of life cycle productivity of Malaysian oil palm by mapping the annual output FBB over a 22-year
cultivative timeline. Biologically, oil palms do not yield food at a constant rate. Their life cycle follows a non-linear cubic trajectory. So biologically, oil palm do not yield food at a constant rate. Their life cycle follows a non-linear cubic trajectory. So from year 3 to 5, initially vegetative and establishment with low food output. Year 6 to 10, explosive exponential growth in canopy size and photosynthetic efficiency, leading to a peak yield. Lastly, years 11 to 22, a steady biologically decline caused by tall tree height, canopy crowding, shading lower leaves, and reduced cellular efficiency. So the problem requires determining exactly when the plant hits maximum productivity and tracking the velocity of yield adjustment over time using mathematical derivative. So this is the mathematical modeling. Yield function predicts the total annual FFP yield in metric tons per hectare, where the X represents the plantation tree age. And also the derivative rate of change calculates the instantaneous growth rate. Rate tells us exactly how fast the productivity is increasing or decreasing at any given year. So the importance of studying this bioscience problem for a student majority in food security, analyzing these biological growth rates using calculus is vital for several reasons. First, land use efficiency. Malaysia has a strict caps on forest conversion to protect biodiversity to ensure global vegetable oil security without expanding land footprints. Agronomists must optimize production on existing land. Second, precision resource allocating. Knowing the rate of change, sales manager when the plant is hungriest, a high positive derivative means the crop is growing rapidly and requires heavy fertilizer inputs. The last one, strategic replanting cycles. Plantation takes years to mature. By calculating exactly when production decay accelerates, corporate or smallholder operations can plan staggered replanting schedules, ensuring there is never sudden drop in regional food suppliers. So my recommendation to enhance the HTML application is to put the tangent line. The tangent line need to make the tangent line this tangent line to make this web tool significantly more robust for your web development portfolio and bioscience presentation. So the visual connection, the slope of the tangent line is the derivative. When the user click year 6, they would see a steep line pointing so they would see a step line pointing sharply upward. When they click year 9 to 5, the line would become perfectly horizontal. So when they click year 18, the line would tilt sharply down. So at year 22.0, the system in the structure decline. From a food security standpoint, this step negative rates indicates the plot is consuming fertilizer inefficiency and should be earmarked for systematic replanting. That's it from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, my name is NURALIA SYUHADA binti ABDUL. My metric number F25A1740. Today I want to present our project Oil Pump Scrap Bio-Derivative Simulator. Today demonstrated how we apply calculus to solve article issue in the Malaysian agro industry. This project focuses on the oil pump elastic renaissance. As you can see from my research, oil accumulation in the fruit follow a non-linear peak model trajectory. In the field, grower face a difficult dilemma: harvest too early and you get a low oil accumulation because the fruit has not matured. Harvest too late and the fruit rot, leading to an increase in free fatty acid, which ruins industrial quality. The challenges in finding the Goldilocks window from harvest. It is vital because the oil pump in the cornerstone of Malaysian economy, relying on manual visual estimation of weakness and subjective, and often lead to significant economy loss. By applying mathematical modeling, we move from gas to precious. This tool provides an objective, scientific baseline calibrate against MBOB standard, allowing us to predict the exact biological state of fruit to ensure we harvest at the moment of maximum yield. That you can see, the green line represents to the total lipid content, and the red line is derivative. It tells us the speed of oil accumulation. Many think we should harvest the peak of the red line, but our model shows that when accumulation is fast, not when it's finished. How? As I move to the slider, 21.7 or 26. Notice the started flat line near zero. This is the optional window where oil is stable and maximum yield is guaranteed. This changed our operational decision from an observation to a mathematical pattern. To make this tool even better, I recommended integrating live weather data, since precipitation management, like water, directly affect the acceleration rate. Having the simulation automatically adjust its value based on the real-time rainfall or irrigation data would make this a truly smart farm application. That's all from me. Thank you.